You can kill me, but you've got nothing on that guy. I mean, he's literally stacked.
Hello everybody, and welcome back to Beau Maths. It's been quite a while, and I missed you, and I'm sure you've missed your frequent dose of Beau Maths. But in any case, we're back, and today we're going to be talking about a really interesting topic. And typically this isn't something that's covered in math, it's usually covered in computer science. However, I have two reasons for covering it. First of all, it's just interesting and I want to talk about it, so why not? And secondly, it will have a nice connection with some of the math we've been doing. As you can see here, this says both stacks, which is the computer science bit, and postfix notation. So that's going to be relevant right here. And one thing to note is that I'm just having a little bit of camera issues right now, so I will at some point be returning to, my classic pen and paper. But for the time being, we're going to have to deal with a little bit of computer. Which I guess is alright considering this is a computer science themed video or an application to it. Stacks. So the idea of a stack is it's a way of storing data, and it does it in a specific way, namely like how we would stack things. So for example, let's say I have a piece of data like the number 17, and let's say I want to store it, so I put it into my stack. Okay, so now somewhere in my computer, there's this stack or this entity that is storing this 17. And then maybe I want to add another piece of data, but it doesn't have to be just a number. Maybe it's a name, right? So maybe I add the piece of data Beau Maths onto it. But notice I've kind of stacked it on top of the 17. Then maybe I can add another piece of data. Maybe it's the letter A. Then let's say I want to access Beau Maths. Well, if we think of a stack of things, right, a stack of plates, it's hard for me to get to the second one without getting rid of the top one first, right? And so the way a stack works is we can only add to and take away the first piece of data. So if I want to get to Beau Maths, I have to remove the A first. And now I can access Beau Maths because it's the top piece of data. So just like how we normally stack things, this is kind of how a stack works. And so I can just pop this up right here. A stack is a way of storing data where you add to the top and you can only access the first or the top piece of data. So you may wonder, okay, what's the point of this when we could just have something where we can access all pieces of data? And a lot of reasons for this is efficiency. If you only can add to and access the top piece of data and you're able to work around that, then you don't have to spend time sifting through all of your data. You can always just access what is immediately there, right? And so a lot of computer algorithms, they make use of these stacks in order to really speed up the processes of what's going on. So if you're able to work with the stack structure, you can do things a lot faster. Now, there's a couple names or a couple operations that are associated with this stack. The first one is the push operation. So that's the action of adding data to the top of the stack. So when I put the A on top of the stack, when I put this piece of data on top, we say that I am pushing the data onto the stack. And if I want to remove data, we say that is popping. So when I pop data from the stack, that's the action of removing it from the top. So if I pop from the stack, I am popping the A off the stack. Then maybe I'll pop the Beau Maths off the stack. And we can do this back and forth, right? Maybe I'll push some data on and push another piece of data on. Maybe I'll pop a piece of data off and maybe I'll push another piece of data on, right? So it's just a matter of adding and removing, but only from the top. I can't access the 17 unless I've popped off the data on top of it, right? And I can pop everything off the stack and now my stack is empty, right? So we kind of get an idea for how these stacks work. You push data or you add data to the top, just like you do when you're stacking things. And when you remove things, you can only remove from the top. Okay, so that's how stacks work. Now let's get into how they affiliate with postfix notation.
Stacks and postfix notation.
So let's just do a quick recap of what postfix notation is. And if you're really unsure about it, I recommend going back and watching my video and the exercise video that I have on postfix and prefix notation. But just to recall, normally we write things in what's called infix notation, where we put the operator between our operands, or between the 3 and the 4. But with postfix notation, we just change the order and we put the operation afterwards. But both of these expressions are still saying the same thing. we're taking a 3, we're taking a 4, and we're combining it with addition. It's just how we go about writing that. The order in which you do that changes. Okay, so we could look at an expression like this just for a little practice. For with postfix notation, we always evaluate the operations from left to right. So we start by evaluating this multiplication, which is affecting the two numbers to the right of it, to the left of it. So that's just 4 and 5. So 4 times 5 is 20. So that was this piece right here. And then we still have our 3, our 1, our plus, and our minus. Okay, the next operation is the plus, so that's affecting the two numbers to the left of it, so the 3 and the 1. The 3 plus 1 becomes 4, right? So we get 20, 4, and then minus, right? So this 3, 1, and plus became this 4, so that disappears. And then lastly, we just have to worry about this operation of 20 minus 4, which is 16. So that is how we would evaluate this postfix notation expression. Again, if you weren't familiar with that, I just did this really quickly. Please go back and watch the videos where we talked about postfix notation. Okay, so now how does this connect with stacks? Well, it turns out we can use a stack to actually evaluate expressions in postfix notation. And the way we do it kind of follows these steps. When we input a number, we push the number onto the stack, okay? And when we input an operation, we pop 2 from the stack and then evaluate. Then we would push the result back onto the stack. So let's go through what this means with an example. So let's say we're working with this postfix notation here, and we want to evaluate it using a stack. So we just read from left to right in terms of how we've input them, and we see how a stack will work really nicely with how things work. So we just follow the rules. When we input a number, which is what we're doing first, we just push it onto the stack. So here we have a 1, so I'm going to push a 1 onto the stack. Then we have a 3, so that means I have to push a 3 onto the stack. Next up we have a 7, still a number, so we're going to push a 7 onto the stack. Okay, now at this point, when we input an operation, right, so our next operation is multiplications, we've input that, we're going to pop 2 of the data from the stack, right, because the operation evaluates the 2 data to the left of it. So popping 2 data from the stack is like us selecting this 3 and 7, so we're going to pop the 7, pop the 3, and then we're going to evaluate it with the multiplication. So once the computer calculator does that, then we get a 21 and we push that onto the stack. Okay, so now our stack looks like this, and that covered all of these inputs here. The next input we have is the plus. When we input the plus, once again, this pops the next 2 data from the stack, so the 21 and the 1, and it combines them with addition, which when it does that, we get 22. And it pushes the 22 onto the stack. And now that we're done inputting things and we have 1 number left, we're done. So our result of our input was 22. And so this is how some computers and some old calculators actually used to, and maybe sometimes still do, calculations. And you see that basically all we have to do is just read from left to right with our input for the postfix notation. So a little bit differently than how we would evaluate this just when we're doing it with our own pen and paper. But we see that it works really nicely with the stack. And remember, one of the advantages of postfix notation is that we didn't have to worry about order of operations. Well, now imagine if you're trying to get a computer to figure out how to do order of operations, that can be quite a complicated task. However, if we just use a stack, right, we see that all we have to do is just go from the order in which we input the numbers and the operations, and the stack does all the work for us. And so we see that this is a really nice way for a computer to efficiently evaluate expressions as long as we're comfortable giving the expressions to it in postfix notation.
A moderately girthy example.
Alright, so let's do another example, a little bit more complicated. So we're going to use a stack to evaluate this expression right here. So whenever there's numbers, we just push those onto the stack. So we push a 1 on, and then we push a 7 on, and then next up is a 3, and lastly we'll push a 4 on before we get to our first operation, which is a minus. So we have a minus, so it's an operation, meaning we pop the last 2 pieces of data. Remember, that just corresponds to us saying, okay, we take the operation and look at the 2 pieces of numbers to the left of it. So we're doing that with the data here. So we pop the 4 and the 3. And when we evaluate them with minus, we have to keep in mind the order in which they come in, right? Just because I've popped it in this order here, it might make it look like 4 minus 3, but the computer needs to know when we're coding this that it's going to be in the original order, right? Which was the 3 and then the 4 that we're doing the subtraction, right? So we're really doing 3, 4 minus. And what does that give? Well, 3 minus 4 is -1. So we get -1, and we're going to push that onto the stack. All right, next up we have another operation of plus. Okay, so we pop 2 times off the stack, so that gives us our data of -1 and 7. And when we add them together, -1 plus 7 is 6. So we take that result of 6 and we push that onto our stack. Okay, what's the next piece? The next piece is another 6. So we're going to push the 6 onto the stack, right? That's just from this input right here. Okay, and then we have multiplication. So we're going to take the multiplication operation. It being an operation means we have to pop twice off the stack, so the 6 and the 6. 6 times 6 is going to be 36, right? So we've completed that evaluation. And so we can push the resulting 36 onto the stack. So you see this has a really nice flow to it, right? Push data on, operation, pop twice, evaluate, push back on, and just keep on going, right? And so we could infinitely add to this expression if we wanted to, right? And this stack is just going to kind of keep a running tab of what the result is as we go. Okay, so what's the next piece? The next piece is minus. So we take a minus, which means we're doing a subtraction. So we pop the 36 and the 1, keeping in mind to have the order where it's the bottom to the top, right? That keeps the original order of the numbers in which they occur in our expression. The 1 came first, so we have to do 1 minus 36, which gives us minus 35. So that means we're going to take minus 35, which is the result, and push it onto our stack. Okay, next up, we input a 5. So that's just pushed onto the stack. And lastly, we have division. And division is going to be our operation that pops the 2 pieces of data from the stack. And once again, we have to do it in the right orders. So the 5 was input after the minus 35, right? So we actually have to do the evaluation in this order. Minus 35 divided by 5 is minus 7. So then we take the minus 7 and we push it onto the stack, and that is going to be our result. Okay, and again, we could keep adding to this, right? I could say like 3 plus, right? And then, okay, I'd have to push a 3 on, do the plus, and kind of go from there. But we see that we're able to use stacks to kind of evaluate these postfix notation operations from left to right.
Calculator use.
So as I've said, computers and calculators sometimes use this in order to evaluate expressions quickly, so you don't have to have the computer worry about how to do order of operations or anything like that. It just kind of evaluates it as you put things into it. And so a lot of older calculators, they were called RPN calculators, reverse Polish notation, right? That was another word we used for postfix notation. These calculators here, they actually required the user to input them in postfix notation. So if I wanted to do 3 plus 4, I wouldn't click 3 plus and then 4. I would actually do 3, enter, 4, enter, and then I would do plus, right? Because that is me doing this in postfix notation, because this calculator was actually hardwired to evaluate expressions in postfix notation, not in fixed notation like we're used to a lot of calculators doing now. So if you find some old calculator, you may actually be required in order to use it to know how to use postfix notation. So it actually used to be quite a lot more relevant to people using these devices.
Concluding thoughts.
Okay, well, that's going to do it for me today. I hope you found this video interesting. I think this is a really cool topic where we're kind of using this very intuitive structure of just putting one thing on top of another, and we're using that in order to evaluate these expressions in postfix notation, and we see it works really nicely. This enables us to understand how stacks work a little bit better, because they have way more uses than just postfix notation, but B, it also allows us to appreciate how postfix notation really can be used with computers and calculators, and it's not just kind of some goofy little thing that we came up with that doesn't really have much application, because this shows that we can very easily implement postfix notation into our computers, into our calculators, by using the power of stacks. So that's going to do it for me today. I hope you had a good time, but until the next one, you have a good day. You stay groovy, and I'll see you in that next Beau Maths video.
I just spent half an hour trying to stack these.
Beau Maths.